Oh, there's more. Right? We have a seemingly innocent-looking trig equation like sine of x equals 1 plus cosine of x. Looks like, well, this one isn't going to be too much of a problem, but if you look at all the techniques we talked about so far, there's really nothing that this falls under the category of. If you say, well, let's isolate. Well, okay, I can isolate sine, but that doesn't really isolate. It's not isolated equal to a constant, so forget the square root property also. Factoring opportunities are nil. And don't say, oh, do we have a substitution for sine and cosine? You do, but you don't want to see it. What is sine? Well, we can call it 1 minus cosine squared, square root. I don't think you really want to do that. That's not a good substitution. So never did that before. Let's not start now, because that's really not the technique we're going to use here. We're going to use something that is kind of the reverse of the square root property. That is, take both sides to the second power. Because if we do that, if we take both sides to the second power, at least we have something to work with. We'll have sine squareds and cosine squareds and some other things that will come along for the ride. But at least we can handle that and, have some substitution opportunities or factoring opportunities that, we might need. So in this case, I am going to do something very daring and square both sides. Square both sides of this equation. Now that is a technique that we do have to be careful with. We have done this to equations in the past, not trig equations, but equations in the past. You say, no, we haven't. I say, yes, we have. Square root of x equals 5. That's called a radical equation. What gets rid of a square root? Well, squaring. So we would square both sides of this equation, if you remember. And that gives us x equals 25. Now, the only problem when you square both sides of an equation, you can introduce what we call extraneous. Remember those extraneous roots? They can happen, and they will happen. You square both sides. They can and do happen for the even roots. So if you cube both sides, no worries about extraneous. Fifth power both sides, no worries about extraneous, but any even power to both sides of a radical equation, you do have to watch out for. The idea is squaring both sides of an equation can be dangerous. And I can show you a simple example. It doesn't illustrate much except for how you can end up with some false information here. If I said x is equal to -5, for example, and I squared both sides of this equation, I would get x squared equals -5 squared. I get x squared equals 25. Now, if you try to solve that equation to get back to this answer, you actually get two answers to this. Solving it, you get x equals 5, x equals -5. 5 would be called extraneous, because that was not my original solution. My original solution was x equals -5. But you can see squaring both sides of an equation can kind of bring along some extra stuff for the ride, some extraneous. So the moral to the story is when you square both sides, watch out for extraneous. You say, well, what do you mean watch out? We actually have to plug our solutions back into the original to make sure that they do in fact work. So it's just one of those things, one of those techniques that we do have to watch. All right, so if we square both sides of this equation, we'll just call this sine squared x on the left. On the right, no shortcuts here. We're going to have to write that twice. We're going to have to FOIL it. So sine squared x equals, writing that twice and FOILing it, you get 1 plus 2 cosine of x plus cosine squared x. All right, so at least we got some sine squareds and cosine squareds to work with. Subtracting cosine squared does not produce a very particularly good identity for us, or for that matter, subtracting sine squared. I mean, if I could get a sine squared plus a cosine squared, that would be 1. That's not what we're going to get here. So what we can do is say, okay, we got a cosine squared, we have a cosine to the first. I'm not changing cosine to the first to anything. It's going to have to stay cosine. However, sine squared we can change. So why don't we at least get agreement on this problem and go with all cosines. So 1 minus sine squared, we know from the Pythagorean identity to be 1 minus cosine squared of x. And now, at the very least, we're all, well, both sides are in the same function. And that would be cosine. Right? Looks like we're going to want to get everything on one side of this equation. So I'm going to add cosine squared to both sides. Let's put it right underneath its like term. And subtract 1, do the same. Right? What do we get? Well, left side we do get a 0. Equals the 1's cancel on both sides. And I get 2 cosine of x plus 2 cosine squared x. Right. Now you notice here we have factoring opportunities. So 0 equals, factor out the GCF. We're left with 1 plus cosine x. Set both of our factors equal to 0. 2 cosine of x equals 0. 1 plus cosine of x equals 0. So divide by 2, still get 0. Subtract 1, I get -1. All right, these look to be quadrantals. So if you look at your cosine graph, that might be super helpful here. Quadrantals, look at your graph. We got 2 pi, we got pi, and you know how cosine works. So let's draw it. Cosine inverse of 0. Well, if we're looking for principal values, I guess we might as well keep with the theme. Cosine inverse of 0. Well, it's got to be something between quadrant 1 and quadrant 2. It's got to be within that range from 0 to 180. So what are we looking at? I believe our one and only option is pi halves here. Right? That's where cosine is actually 0. So cosine inverse of 0, principal value, yeah, it's going to be pi halves. If we're talking radians, if we're talking degrees, sorry. Just stay fluent in both languages. Right, here, cosine inverse of -1. Between 0 and pi, including pi, and we do have to include pi, that's going to be our value there. The cosine inverse of -1 is pi, or 180 degrees. Now again, these principal values can be found directly on the calculator. That is the principle your calculator works on. You know, I should take my word for this, but just to show you, if I do a cosine inverse of 0, right? Okay, what did I do? My mode. I am in radian. This is why it's so important that you get in the right mode. So second quit. Try again. Bada bing, bada bang. 90. We're talking pi halves or 90 degrees. Right? Now if we do the cosine inverse of -1, it goes to the very edge of its domain, which is 180 degrees. Again, look back at those videos for that cosine inverse when we first talked about that. Right? So we do get those same values. All right, so if we go 0 to 360, here's where the graph really pays off, particularly on these quadrantals. So less than or equal to 360. All right, if we go 0 to 360, where is cosine of x? I should not be pointing at this. I should be pointing at that. Where is cosine 0 at? Well, it's 0 at pi halves. It is also 0 at 3 pi halves. Fact. So pi halves, 3 pi halves. If you're talking radians, if you're talking degrees, we're looking at 90. We're looking at 270. Right? Where is cosine? Oops, keep pointing to the wrong thing. Don't point to this, you point to this. Where is cosine of x equal to -1? Well, we saw it at pi. Where else? Well, it's not going to be -1 until way over here, past 2 pi, and -1 back over here, which is past 0. So we're looking at just one solution. Nice job. That's 0 to 360. Obviously, that's 0 less than or equal to x, less than or equal to 2 pi. Please forgive me. All right, we're good. All right, so we're going with pi, or we're going with 180 degrees. Again, 0 to 360, 0 to 2 pi. All right. Now, we can't just say done and done. There's our solutions. Before we could, but when you square both sides, there's extraneous possibilities. What does that mean for us? Unfortunately, that means we got to check these solutions we're getting. 1, 2, 3 solutions. Do we really have 3 solutions from 0 to 360 or 0 to 2 pi? Well, let's check our degree solutions. It's not going to take that long. You just simply plug it in there. So step up, x equals, let's talk degrees. Is 90 degrees a solution? So question, if I take the sine of 90, does it really equal 1 plus the cosine of 90? And let me see. What is the sine of 90? Sine of 90 I know is 1. Cosine of 90 I know is 0. I'm going to go and say, yeah, 90 is good. So 90 is definitely one of my solutions. Next, step up to 70. So x equals 270. Are you a solution? Well, take the sine of 270. Does that equal, question mark, 1 plus the cosine of 270? Well, sine of 270, oh no. Keep going. Sine of 270, what are you? Well, you are -1. Cosine of 270, you are 0. So -1 equals 1 plus 0. I don't think so. 270 is extraneous. Don't count it in your solution set. It's not a solution. It's a bad answer. All right, so that came along for the ride. It came out of squaring both sides. That sometimes happens. You drag along things that aren't solutions to the original. All right, final. We got 180. Are you a solution? Well, if you take the sine of 180, will that equal, question mark, 1 plus the cosine of 180? Well, let's see, sine of 180, big 0. Cosine of 180 is, pi, -1. I think that is a true statement. So 180, I believe you're good. We have 2 solutions to this equation. Just watch it. When you square both sides, you could definitely get extraneous solutions. So, got to check them from your original. It's not a terrible check. Just plug them back in, make sure they actually do work.